Hello everyone, so this is going to be example problem 1, and before we get started I'm going to go back to our DC and AC series Venn diagram. I'm simply going to circle what we're going to use and focus on in this problem. So in this first problem we're going to focus on Ohm's law, on current is the same and continuous in our series circuits, total impedance ZT, and voltage and current changes due to time and frequency. We're going to touch on that a little bit here. The example problem is on the right side of the screen. Feel free to write it down and solve it when I go through it. First things first, I'm going to look at our current source. And this is our current source. It is modeled by this squiggly line, which is meant to represent a sinusoid. And then it has an arrow through it. And then we're giving a sinusoidal equation. Before we get started, I'm going to write a little reminder of what the typical form of an AC sinusoid is. So we would usually have a voltage value, or we can have a current value, and then we will have sine omega t, and then plus theta. And that's typically our sinusoidal equation. To explain these in different terms, we can break down each part. The V or I, this is always a value and it's a magnitude. It's representing how much voltage or how much current we have, and then it's multiplied by the sine wave, so that's how much it's fluctuating. A lot of times we can describe this in peak values. Here it's given us in pk, so we know it's a peak value. And that's telling us in our sinusoid, this peak value is that magnitude. So from 0 to this max point is our peak value. So that's what that's telling us. We also have this character called omega. It's a Greek letter. And omega is talking about the frequency. It is also called the angular velocity. It's represented, the equation for omega is 2 pi times f. In this case, we didn't get the frequency, but it won't be that important for us solving the problem. And the last thing we have a part of our sinusoid is this theta value, and theta is the phase shift, and it can be a positive phase shift or it can be a negative phase shift. So whatever sign this theta has, it can impact the sign right before it. But this is a typical form of an AC sinusoid. So now we can break down our current source and see what we have. So we know we're given amps right here at the end, and we know it's a current source. So I'm going to write down we have 8.42. This is amps peak. We also have this 40 degrees, a positive 40 degrees. This is our phase shift. So our theta is equal to 40 degrees. And our omega t, we can't find the frequency from here, so I'm going to leave it as is. And when I'm going to think about my math, I want to be in polar form or phasor form. So I'm going to go ahead and write that out. So quick recap, we just did a small review on an AC sinusoid equation, and then we broke down our current source. So now that we've done that, let's start breaking down our circuit. In this circuit, we can see it is one continuous path. So this I from the current source, this IS, is equal to the I total. Once again, we are still working with series circuits in this AC, and this current is going to be at the resistor. It's going to be the same current at this inductor. So the I from the source is the I total. Okay. And I have that written right here. Okay. And something else I notice, I have an ohm value for my resistor, and I have an ohm value for my inductor. In DC, we always had resistors, and it was always easy to add up 10 ohms and 5 ohms when they're in series. Here, we can't think about resistances, and an inductor and capacitor are our reactive components, so we can't just add them up directly like that. We have to do a little bit more thinking. And if you remember from the last slide, that's where we talked about ZT. And ZT is the total impedance. We do know that the total impedance will be, in series, the sum of each component. So the impedance of the resistor plus the impedance of the inductor. So whenever we talk about impedances, we want to think about the relationship that that component has with the voltage and current. For a resistor, the voltage and current at a resistor are always in phase with each other. So I'm always going to have an angle of 0 degrees. So the impedance of my resistor is just going to be 29 ohms. I can also write this 29 ohms angle 0. Okay? And then for our inductor, we are thinking about a phase angle of positive 90 degrees. And they already gave us our reactance value, X of L, reactance. So I can write 5 ohms of 90 degrees. Five ohms of 90 degrees. Okay? And so now to find my total impedance, I can add those two values up. And that value I will get is going to be 29.4 ohms, angle 9.78 degrees. Okay. Before we keep on going with these values, I'm going to explain my thought process of finding the total impedance. Remember that in Ohm's law, it's always component specific. So in my regular equation in DC, voltage equals I times the resistance. If this was the voltage of a resistor, I would need the current of the resistor and the resistance of that resistor. We can say R1. Same idea applies here. In this case, let's say I want to find the voltage of the inductor, the voltage of the resistor, and the total voltage. And what I would need here is the current at the inductor and the impedance of the inductor, the current of the resistor, and the impedance of the resistor. And then finally, I would need the current total and the total impedance. So I was able to find all three of these impedance values, which is great. And I was also able to find all three of these current values because once again, my circuit is in series. So this current value is going to stay the same for each and every single one of my equations. So let's go and start finding those values. So we're going to have, we can start with voltage of the inductor. We're going to have the current. We said 8.42, and this is amps peak. Angle 40 degrees. We are multiplying this by the impedance of the inductor, which is going to be 5 angle 90 degrees. And this is ohms. The answer we will get from this calculation is going to be 42.1 volts peak, and its angle 130 degrees. Before I move on, I'm going to do one quick check. If this is my final answer, something I realize is, if my current is 40 degrees and my voltage at my inductor is 130 degrees, I have a positive 90 degrees shift between those two. My voltage is leading my current, this is my current, by 90 degrees. This makes sense with what I said about the impedance of my inductor and also makes sense with our acronym, Eli, the Ice Puppies. So Eli, the voltage in an inductor leads the current. So that's a good way to check my work. Okay. Now we are good to start the next problem, or start the next part of this problem. Let's find the voltage of the resistor. Same idea. We're going to take that same current value, 8.42 amps peak, and this time multiplied by the resistance, and the resistor was 29 ohms. Yep, 29 ohms. Okay, let me make sure I include my angle here. It's going to be 40 degrees. And this is to find the voltage of my resistor. After I do this calculation, my voltage of my resistor is going to be 241.8 volts peak, angle 40 degrees. Once again, before I finalize my answer, I can see for the current and the voltage of my resistor, they both have a phase angle of 40 degrees. The voltage and current are in phase at my resistor. And that is what I want to see. For this last calculation, we're just going to do the voltage total, which is going to be the current total times the impedance total. So we're going to have 8.42 amps peak, angle 40 degrees, times the total impedance. The total impedance, we calculated it above by adding the two impedances of the resistor and inductor. And it was 29.4, angle 9.78 degrees. For our V total, we will get a value of 247.78 volts peak, angle 49.7.